Hello everyone, welcome back. In today's video, we want to discuss partial differential equations. Now, partial differential equations is a topic that deserves its own subject, and we'll probably make a course on that. But for now, we've only got multivariable and single variable, so we're going to talk about this in about a video. I want to discuss a specific partial differential equation called the Laplace equation. This equation is extremely important in the field of physics, where it's used for electromagnetism and signal processing because of the properties of the function that it that satisfies this equation. So let's just talk about this. This will be a fairly quick video. We'll go over the definition, then we'll try an example. And then we're kind of done with our brief introduction to partial derivatives, or introduction to partial derivatives, which, well, I guess hasn't been super brief, but it's been very important nonetheless. Anyways, the Laplace's equation says that the second derivative of u with respect to x is plus the partial derivative of u with respect to y is plus the second partial derivative of u with respect to y is equal to 0. Okay, so basically what this says is partial squared u over partial x squared equals partial squared u, or negative partial squared u over partial y squared. Now, if this were a single variable equation, when we see the partial squareds, or when we see the second derivatives being equal to something else, being proportional at least, that usually brings the wave in mind, like a sine wave or a cosine wave. Well, it turns out that a solution to Laplace's equation is usually a form of wave equation, so a form of harmonic equation. So actually, you call equations that satisfy Laplace's equation, you call them harmonic. So that is what a harmonic function is, a function that satisfies Laplace's equation. Anyways, let's see if the following function is a harmonic function. So do we solve Laplace's equation? Let's say that f of x, y equals e to the x sine y. So what we want to do first is we want to gather all of our partial derivative terms. So we'll gather our first order terms. Our first order term says that partial f by partial x is equal to e to the x sine y, and partial f partial y is equal to e to the x cosine y, because you differentiate the you differentiate the sign and you get a cosine, obviously, right? And then we take all of the other partial derivatives. So we take partial squared f partial x squared equals e to the x sine y. Then partial squared f partial x partial y equals e to the x cosine y. And then by what we proved yesterday, that's going to be equal to the other cross term, e to the x cosine y. And then finally, partial squared f by partial y squared is equal to negative e to the x sine y. So you can see what we're dealing with is we're dealing with this guy here, and we're dealing with this guy here, because these aren't important to Laplace's equation. So what we get is that it does satisfy the partial differential equation, because when we add the x derivative with the y derivative, then we're equal to 0. So we have found a harmonic function, and this is what it looks like. It looks fairly wavy. So that is how a partial second order partial differential equation works. So we've just solved a partial, or we've tested a partial differential equation. So that's pretty cool. In the next video, we're going to introduce tangent planes. We'll see you here next time. Bye.